Okay, so we were talking about permanent magnet sensors. Also, some of you did the labs on the sensors. I graded those this morning. So between what we talked about last week and what you saw in the lab, should have drawn the pieces together for you. So a permanent magnet sensor could be used to measure which of the following. So you can use the chat or speak up.
Is that number 3? No.
It is not. Number 3 would be
sorry.
thermistor. So
Thermistor,
a thermistor is the variable resistor we talked about last week that measures temperature, where we have 2 resistors in a series circuit, one inside the computer and the other is the negative NTC thermistor that we have measuring temperature.
I
So if
think
we're going to measure temperature, we're probably going to use a thermistor. A permanent magnet sensor can only be used to measure something that rotates.
the crankshaft rotation, throttle position.
So throttle position, our throttle
position.
we're not rotating our gas pedal, we're just moving it back and forth. Manifold pressure is a pressure measurement. We haven't talked about that yet and how we do that, which really leaves us with the crankshaft rotation.
Crankshaft.
Right, number 1, because that is something that rotates. The crankshaft goes around and around. So permanent magnet sensors can only be used for something that's spinning around. I can't measure something that just moves back and forth because it's an analog sensor and we need a certain amount of speed to get the amplitude and frequency to where we have enough that the computer is able to see it. If I don't have enough amplitude because it's moving too slowly, then the computer won't see it.
Yep.
So crankshaft rotation for that one. So although vehicle speed sensor and the rear differential performs a very different function for the PCM than the crankshaft position sensor, electrically they are the same and they can be tested the same way and must operate within the same rules. If you're testing a permanent magnet sensor, it makes no difference what its function is once you understand the operation. So here is a vehicle speed sensor that would be put into a differential. And so it is going to work the same way. It's going to generate that AC waveform. We're going to take a look at it. The only difference we see in sensors for wheel speed sensors or vehicle speed sensors, ABS sensors, is that they aren't missing teeth, because I don't need to know when the wheel comes around to the valve stem, right? I don't need to know that. So I'm only measuring, is it going around and how fast it's going around. The crankshaft is going to be missing teeth, so we have that separator signal so we can figure out where top dead center is for timing. So that's the only difference. The sensor works the same way, but the reluctor wheel that's spinning around that it changes the electromagnetic field, that's going to be different on a crankshaft than it would be a wheel speed or vehicle speed, because I don't need to know every time it goes around. So here is a vehicle speed sensor and a differential. Here's another example of a wheel speed sensor for the ABS system. So if it's a permanent magnet sensor, it's a permanent magnet sensor. We're going to test it the same way. So what kind of electrical signal is created by a permanent magnet sensor? I did just say it, didn't I?
Number 3, square wave.
No, it would not be number 3, square wave. A square wave is another name for a digital signal. So a digital signal has a clear low and a clear high. And when it goes from low to high or high to low, it makes a square because it's either low or high. Our crankshaft sensor makes that wave like this on a permanent magnet sensor. So that would be an analog signal. So number 2, analog. So permanent magnet sensors make an analog signal. A square wave is another name for a digital sensor signal. So all square wave signals are going to be digital. A digital signal is going to be square wave. So it's kind of like 12 and a dozen. So a lot of times they'll use both of those answers as distractors here to come up with 4 distractors when they're not the right answer. So because they mean the same thing, digital and square wave mean the same thing. And then steady voltage would mean it what never changes. Well, that can't measure anything. Because then I need to use current or something else if the voltage stays steady. So analog signal. So let's look at a pressure switch. So a pressure switch is going to work like any other switch, except for instead of our hand turning it on and off, pressure turns it on and off. So I can make a pressure switch that turns on with pressure, or I can make a pressure switch that turns off with pressure. So we make them both ways. We use them both ways on cars. So looking at the wiring schematics important and understanding how this system that's being measured functions as far as how the pressure in that system, whether it's power steering or transmission or oil or whatever it is, we're measuring the pressure with a switch. So pressure switches typically are 2 wires, although some are a single wire and are grounded through the threads. So a lot of oil pressure switches are that way, where they are grounded through the threads and there's only 1 wire going to them. And it's located in a location where fluid pressure monitoring is critical. Common uses: air conditioning, power steering, engine oil. So I want to know how much pressure I have in my air conditioning system because I don't want to blow my compressor up from too much pressure, and I don't want to damage it from running it empty with too little pressure. Engine oil, right? We want to let you know, or newer cars will actually turn the engine off if we lose oil pressure. And then power steering. And you might be thinking about, why do I care about power steering pressure? Well, engines today are pretty doggone small. And the idle speed is controlled by the computer. So if I have power steering that uses hydraulic, so we're not talking about electric power steering that we're using today on many vehicles, but a standard hydraulic power steering system. When I turn the wheel all the way to the end, you'll hear a noise, and that is because we're hitting the maximum pressure of the system. As we hit the maximum pressure of the system, we put more drag on the power steering pump and more drag on the engine, which can lug the engine down or actually cause it to stall. So the computer is going to raise the engine speed up to make sure it doesn't stall. So that is one reason we need to know why we're lugging down. Hey, I need to give it a little more RPM because you're using the wheel really hard. The other is that we might not want to turn on the AC compressor while your steering wheel is cranked. Because if your steering wheel is cranked, you're probably trying to park someplace because you only do that at low speed. And when you're trying to park, you want to go fairly slow and think about what happened if you're parking and all of a sudden someone gives it gas when you're not ready to give gas. You might lurch forward and hit something. Well, as the AC compressor turns on and off, that also creates a load on the engine or takes a load off the engine. So if we release the AC compressor, the RPM would go up. That might cause the vehicle to surge forward. If I engage the compressor at the same time the power steering is max, it might be too much and actually stall the engine. So we need to know what you're doing. So not all vehicles use a power steering pressure switch, but many do. And they do it so that they can better control idle speed and ultimately so the vehicle's safer. So it's not going to stall on you and it's not going to lurch on you when you're trying to maneuver it at low speed. This is not a variable resistor, but an open closed switch, hence the name. Depending on the engineer's design, the circuit of the switch may either be open or closed at the rest position. So one way to find that out would be look at a wiring schematic. When we look at a wiring schematic, I can see the power steering pressure switch here. I have a signal here at the computer and I have ground. So I have ground that goes up to here. When the switch is closed, I'll have ground on both sides. If the switch is open, then I would have power at this side and ground at this side. So inside the computer, what they're not showing you is there is a voltage supply to a resistor. The resistor is the load. And then they're going to measure the voltage between the resistor and the switch. And when the resistor has high voltage, means the switch is open. When the resistor has low voltage, means the switch is closed. So they're not showing you what's going on inside the computer, but think about it. If I apply ground somewhere, it's going up. What do I need for a circuit to operate? A load, right? Because I have to have power, load, and conductors in order to make a circuit. So they're not showing me the load here. That means it has to be inside the computer. Does that make sense to everybody? This is what gets people.
Yes, sir.
What's that? I'm sorry, I talked when you did. What was that?
You said yes.
Okay, thank you. Yeah, and that's why I went back in the beginning of electrical, what we need for a circuit: power supply, conductors, and a load. And so when I look at a wiring schematic here, I see a switch, I see a ground. So I know the computer has to have power in it, and I have to have a load. Since I don't see a load outside the computer, the load has to be inside the computer. And I think that's what makes electrical a little confusing for people sometimes when we move from the classroom out to actually looking at cars, because the schematic doesn't always show you everything in the circuit. It goes into these magic boxes with smoke in them. And if we do something wrong, we let the smoke out. We need a new expensive magic box. So that's why it's really important to understand what's going on, because even if I didn't know if this was normally open or normally closed, would it be reasonable to assume that in one position, both these should be the same, and in another position, they should be different electrically, right? So if I go and check it, say it's a power steering switch, and I'm sitting there idling without my wheel turned, I check pin 1 and pin 2. If they're both the same, when I turn the wheel all the way to max, now they should be different. The switch should have opened. If they're different when I turn the wheel all the way to the max, they should be the same. So again, it's an open closed switch. So I can apply this simple logic to a switch circuit. Once I know what it's supposed to measure, all I'm looking for is, does the switch change? Does it go from open to closed or closed to open at whatever that pressure is that we're trying to control or monitor, I should say, not control. So here's an example of a power steering pressure switch. This is on a Ford, and we can see here the switch is right here on the power steering pressure hose coming out of the power steering pump. 2-wire switch. A switch will produce a voltage change in the circuit when it opens and closes. Is that true?
True.
True, absolutely. And Dante, I got your email. I sent you an email back. Let me know what you need me to do to help you out.
Oh yeah, my account expired. I had it for quite a while. So yeah, it expired.
Okay, just send me an email on that. I'll get it taken care of.
Thank you so much.
You bet. So another type of sensor we have is a variable resistor. This is a rheostat. Most common use for a rheostat is the level sensor in the gas tank. So what we have here is I have ground, goes to a resistor. Connected to the resistor is a wiper arm that's going to connect to different points on this resistor. As I change the different points on this resistor, I'm going to change the amount of current flow through the resistor. Remember, with only one resistor, all I can do is change current flow. I can't change voltage, right? In order to change voltage, I need a second resistor. So what we have here is inside the gauge, there's actually another resistor. So depending on the vintage of the vehicle, It might go to a computer where it's going to have a resistor inside the computer, and it's going to work very similar to our thermistor circuit for temperature, where we have a variable resistor outside, fixed resistor inside. We just measure the voltage difference. That's how we do it today with computerized systems. We still use this rheostat technology. If it's an older system, there's actually a resistor inside here that with more current flow, it'll heat up, it'll bend, causing the needle to move in a mechanical gauge. You still have two resistors in the circuit. So this right here, depending on where it touches, it's going to change the amount of current flow. So if I'm coming in here and only going to the first hump and the arrow's connected over here, very little resistance. If it's connected all the way over here, a lot of resistance. So a lot of resistance is normally, we see empty, and then little resistance is full. So if I wanted to test this system, gauges are kind of hard to test, right? I mean, I just need to tell if they work or not. I don't want to take the gas tank out to look at the rheostat. So what I'll probably do is go to the wires that connect outside the gas tank, disconnect this wire. With it disconnected, I should read empty. If I run a jumper from this wire to ground, the gauge should read full. If it does both of those things, that proves the wiring's good, the gauge is good, and the power supply is good. The only thing that can be wrong is the sending unit in the gas tank. So we don't actually test the sending unit. What we do is we test the gauge and the gauge circuit. If it's all good, the only thing that can be bad is the sending unit. We put a new sending unit in. So this is a good example of how we test a lot of things by exclusion. We prove that nothing else is wrong, then we replace the one part that's really hard to test or we really can't test effectively. And we do this with a lot of systems. But again, it's a pretty quick test because if my gauge is able to read full and empty, we know the wiring works, we know the gauge works. So if it's not working when it's plugged into the fuel send unit, we got a bad fuel send unit. So I'm not worried about trying to check the resistance of the fuel send unit at different places or anything else. I'm just going to bypass it, test the rest of the system very quickly and figure out if it needs it. If it needs it, then a lot of times we have to take the gas tank out to get the send unit out. Here's a picture of a fuel tank send unit. We got two wires here for power and ground, and we have the float that rides on top of the gasoline, and here's our rheostat right here. So if I wanted to test this, this goes outside through a sealed connector to the outside of the tank. All I gotta do is unplug it. Do I read empty? And I can run a jumper from the power and the ground, little paper clip or other electrical jumper, whatever works, and then see if it goes full. If it does, I've just proved all the wiring's good, the gauge is good, send unit's bad. And the reality is sending units go bad all the time because this rubs up and down and it's going to wear out a spot. So if I fill up the tank and then drain the tank down to a quarter of a tank and then fill it up again, it's not going to have as much bouncing or as much movement. But imagine if I run my tank on close to empty all the time. Now it's going to what? It's going to bounce around. It's going to move a lot more. It's going to spend a lot more time in this one area, and eventually it wears out. And that's what we see. All two-wire sensors work by changing the resistance in the circuit they are installed in. Is that true or false?
False.
Which one doesn't change the resistance in the circuit?
Oh. Mm-hmm.
Well, that'd be a permanent magnet sensor, wouldn't it? Because a permanent magnet generates a signal. It's not changing the resistance. The other ones are changing the resistance. So you did get the answer correct. I wanted to know why it was correct. Right? So we got it right, which is great, but I want to know why you got it right. Permanent magnet sensor generates a signal. It doesn't change the resistance in the circuit. A switch changes the resistance in the circuit. A rheostat changes the resistor in the circuit. An NTC thermistor changes the resistance in the circuit. A permanent magnet sensor generates a voltage on the circuit, is not changing resistance. So it is false. But I just want to make sure we understood why. So now let's look at some 3-wire sensor circuits. So we have a lot of 3-wire sensor circuits. We have a lot of fancy names here: mass airflow sensors, manifold absolute pressure sensors, throttle position sensors, EGR valve position sensors, crank camshaft position sensors, just to name a few. We can break these down into just a couple of types of sensors. Mass airflow sensors are unique to just engine operation. It's the only place we use them. So I'll go a little bit into these just because of how they fail and why they go out of calibration more than the internal workings. MAP sensors, I'm not going to get into the internal workings of it all because who cares? But we're going to talk about what it does. I am going to get in the internal workings of the TPS. And the reason why I do that is the TPS allows me to explain how the circuit works. And then once we understand how the circuit works, we can see how that circuit applies to other 3-wire sensors. Because you think about it, we're not opening up these sensors to look inside. We're testing the sensors, externally at the wiring harness or at the computer or using our scan tool to figure out if they're reporting correctly or if they're broken. So I don't need to open them up. I don't need to give you tons of cutaway pictures of this is what's inside. And we certainly don't need to spend an hour trying to explain the inside of a MAP sensor and how a Wheatstone bridge works, which will just confuse everybody. And it doesn't help you fix the car. So there's, even though the book goes into it some, even though other instructors may go into a lot, there's no practical purpose. So when I look at the knowledge that I want to put in my head, I want knowledge in my head that's going to help me fix a car, make my life easier, or make me money. I mean, or cause me enjoyment. And certain things, if they don't meet those requirements, why do I want to learn about them? So I want to get into where we can diagnose the circuit, understand what's happening, and keep it at that level. So I want to look at the throttle position sensor first, and it is called a potentiometer. So we do use some potentiometers on the stereo. We use them very differently on a stereo than we do on a car. We wire them differently, basically. But this is the most common type of position sensor. So if I want to know the position of my blend door, I want to know the position of my EGR valve, my accelerator pedal, anything I want to know, the position of my suspension, how high is my suspension, how low is my suspension, I'm going to use a potentiometer. So anything we're measuring, basically up and down movement, or a 90-degree pivot movement, something like that, we're going to use a potentiometer normally. So most common type of position sensor contains a mechanical arm that is attached to a moving component, throttle plate, accelerator, pedal, air door, etc., which causes it to slide across a fixed resistor within the sensor. So what we have here is we have one circuit and we're measuring it with another circuit. So if I look here, and this is not drawn quite right, the 5 volts should be after the resistor, not before the resistor. But so I have 5 volts that comes out here. My 5 volts comes out, goes through the one load in the circuit and back to ground. That's my circuit. We will always use 5 volts between the A and B connector here. I don't care where the throttle is. We should always have our 5 volts there on a vehicle that uses a 5 volt voltage reference, which all OBD2 vehicles do. If I get into some older vehicles, I can see some other reference voltages, but we call it VREF, and you'll actually see it posted out of the computer as VREF. And this voltage reference will be shared with other 3-wire sensors normally. This ground will also be shared with other 3-wire sensors. The signal return is only going back for the computer to monitor where the throttle is. So since we're always using 5 volts across this resistor, think of my throttle position sensor signal as a digital multimeter. And we're going to measure the voltage present at the different points in the resistor. So if I start with 5 volts and I only go through a little bit of resistance, I should be pretty close to 5 volts. In the middle, I should see 2.5 volts. And close to ground, I should be down around 0.5 volt. So depending on the position, the voltage the computer sees on the throttle position sensor signal is going to change, because all we're doing is we're measuring different points on this resistor. The resistor is always dropping 5 volts. If I'm closer to the voltage source, I'm going to see more voltage. If I'm closer to the ground source, I will see less voltage. So many of our 3-wire circuits work this way, even if they may be different inside. So I use the TPS because I think it's easy to understand testing different parts of a resistor. And actually it's a slide and it goes up and down on the throttle position sensor resistor. So if I'm testing this, I want to always see 5 volts between A and B. And C should change voltage based on throttle position. If I saw this mounted on a suspension system underneath the car, it would still see 3 wires, most likely a 5 volt reference, but I'm going to have a fixed voltage that goes across 2 of the pins, and 1 pin is going to give me a varying voltage based on the angle of the suspension or angle of the air door or whatever else we want to measure. So this is pretty good. And now one of the things that throws people off is that if I have a bad connection at B or high resistance in this wire, the voltage from my signal will go up. And the reason being is this should always drop 5 volts. But if this is only dropping 4 volts, and then this wire is dropping the last volt, and I go down here where I normally see 0.5 volt, now I'm seeing what? About 1.5 volts, because I've got the 0.5 volt here plus the volt here. So it causes the return voltage to go up. So what you want to remember with 3-wire circuits is a bad ground causes your signal return voltage to go up. And a problem on the power side, a problem on the VREF side causes your signal return voltage to go down. So for example, if I'm down here at the bottom and I should be measuring a volt, which would be 80%, I'm 20% of what I have. But if I'm using a volt on the gray wire, now I'm only dropping 4 volts. So now I'm still looking at that same percentage. Well, now I'm going to be down about 0.8 volts. So I'm still measuring the same percentage I'm dropping across the resistor. But if I have less voltage going to the resistor, it's going to change how that reads back. And then that's either going to be taken away from or added to the return signal based on whether the resistance is in ground or whether it's on the power side. So these faults are the same for all 3-wire sensors. So I always want to verify voltage reference. So if I back probe between A and B and I only get 4 volts, I don't care what the signal return voltage is because I know it's not going to be right. I need to find who stole the voltage. This is a series circuit from here through one load back to here. 5 volts is applied. Series circuit rule says my load has to use all my voltage. So if my load does not have all my voltage between A and B, I've got a problem. I've got a voltage supply issue. That's always going to cause the sensor to read incorrectly. Then I would need to do a voltage drop between B and ground and A and VREF. And obviously we check ground first because it's the easiest to check. Getting to the computer takes more time. So here's a couple different 3-wire sensors. Here's our throttle position sensor being mounted on the throttle shaft. Next to it, I have a manifold absolute pressure sensor that we'll talk about shortly. But I want you to notice that I have a green and orange wire and a green and orange wire. I have a black and green wire. I have a black and green wire. So you can see where we have a lot of similarity here. This happens to be white with purple. This one's purple with something else on it, or just straight purple. So you can see where the power is shared, the ground is shared. The difference is the signal return. So if I want to look at my throttle position sensor and test the output of it, I would want to use a lab scope. And the reason why I want to use a lab scope is I want to watch it as with the engine off, open it very slowly and close it very slowly. A lot of times, one of the mistakes people make when they're working on vehicles or working on things, they think in order to find the problem, we need to stress test it real hard, drive it like Mario Andretti. What I can tell you is you're going to find a lot more problems on cars driving it like grandma than you ever will driving it like Mario Andretti. So in the case of the throttle, if I'm looking for a bad throttle position sensor, I want to open it very slowly and close it very slowly. I can only do that with the key on and the engine off. Otherwise, I would over rev the engine and damage the engine. So we can see here, I'm taking about 4.5 seconds. My time is here at the bottom. There's my seconds. Here's my voltage. I'm starting at 0.5 volt. I'm slowly opening the throttle up to about 4.5 volts, slowly closing the throttle, and I'm back down to 0.5 volt. So what I'm looking for is I'm looking for a nice consistent opening and closing with no dropouts. And the voltage I have here should be the same as the voltage I have here. In other words, what I start with and what I end with should be the same. If it's not, that means I probably have something sticking, or I have a bad spot in the throttle position sensor itself, but it could just be a sticking or gummed up throttle where it's not closing the same place every time. Could be a loose TPS where someone worked on it and didn't tighten the adjustment screws all the way. Some of the older ones are adjustable, but that's what we're looking for. So this is a known good one. Now let's take a look at one that's not so good. So here, this vehicle had a problem that when you step on the throttle slowly, it would cut out and want to die. But if you jumped on the throttle really fast, the car would kind of have a little bit of jerk, but it would go. So here I have my 0.5 volt. We're starting to open the throttle. We're continuing to open the throttle, but the sensor tells the computer we just closed the throttle. Then all of a sudden, we snap the throttle wide open according to the computer. We went up to our 4.5 volts, came back down, and as we're coming down, we saw it drop out again and then get back to here. Well, this makes sense because where do you spend most of your time on your gas pedal? Floored or just off idle, right? Just a small amount of gas. So in this example, the throttle position sensor was going back and forth. It finally wore, and it wore a spot where it's not making a good electrical connection. So that's why we see it go up, drop down, and then come back up. So this is a bad throttle position sensor. So you can see this is not a super hard thing to test with the scope or the graphing multimeter, because all I'm doing is key on engine off. I have it connected to my signal return wire, and then I can watch my pattern. Again, I always want to make sure I have all of my voltage available at the sensor before I do this test, or the results of this test are not going to be valid. The TPS return signal wire most closely resembles what meter function? So what did I say the throttle position sensor wire or return wire, signal wire most closely represented? What meter function?
Voltmeter.
Correct. Voltmeter. And just like our high impedance voltmeter, no current is going through that lead. It is just measuring the different points on that resistor for how much voltage drop between 5 volts and 0 volts. So just like our meter is not part of the circuit with current flow, that sensor lead or the sense wire for the throttle position or any sensor, whatever we want to call it, EGR position, it doesn't matter, is not part of the circuit, is not current, is not flowing through it. We're just measuring it. There's a huge resistor inside the computer, just like there's a huge resistor inside our digital multimeter that keeps current from flowing through it. So here's an EGR position sensor. Computer must be able to verify the EGR valve is moving what is commanded. So 3-wire sensor, power, ground, signal return. So again, I'd want to make sure I had 5 volts between power and ground, and my signal return voltage should change as this opens and closes. And this opens and closes with vacuum. So I could disconnect this vacuum hose right here and use a little vacuum hand pump and actually pump it up and watch it move. Now, because nothing is simple on cars, pre-OBD2, so pre-1996, some manufacturers, both Asian and European, used a 3-wire throttle switch instead of a throttle position sensor. So this was used by Mercedes. It was used by other Bosch systems on Europeans. It was also used by Toyota and Datsun on their L-Jet systems. So you will run into this if you work on old stuff. Like I said, nothing in OBD2 is using this. And I bring this up not because I want to test you on it, but because I want you to know it's out there, so that if you have something and you go, wait a minute, this doesn't act anything like a TPS, that's why we have books. That's why when something doesn't look like it's following the rules, go look up and see if the manufacturer did something different on this car. So there's 2 different ways they do this. One is I can have 12 volts going in, and we have 2 switches. So based on whether the car is at idle or whether the car is at wide open throttle, one of these 2 switches will be connected. So this system, these early Bosch systems, whether it's K-Jet or L-Jet, or actually D-Jet also, only cared about, is the throttle closed or is the throttle wide open? In between, we got it handled. We don't care about the throttle other than we're at idle or your foot's to the floor. That's the only thing that computer system cared about. So we used a couple switches. So here we can see we're just sending 12 volts back around. This one's a little different in that we have ground. You're going to see 12 volt here, and then when the switch closes, it collapses the circuit because there is what? A resistor here. So we'd see ground present. So we're either going to switch power or switch ground. It's not so important of what's going on inside. But the key point is it's only measuring idle. It's only measuring wide on the throttle. So there's a lot of Mercedes that did this into the early 90s. There's some Toyotas that did this in the early 90s. Like the Toyota van before they went to the Previa did this. Again, I'm talking old stuff. This is stuff you may never see. But you never know what's going to roll into a shop. So I just want to make you aware these are out there, that, yeah, there are some cars that used a pair of switches in a 3-wire housing. Basically, they're sharing power, sharing ground with the 2 switches instead of a potentiometer. And so I just want to make sure you're aware that these are out there, so that if you're working on something and it's not making sense or it's not following what you expect, especially if it's something old, now it's time to get the old car book. So don't just try to wag it. Don't just try to, figure, oh, I'm sure it's the same as everything else. That's when the clue is, hey, I need to stop, back up. Let me do some research before I go further, or before I start putting parts on the car. Some electrical assemblies mounted on the throttle shaft are actually a pair of switches and not a 3-wire sensor. Is that true or false?
I think it's true.
I hope it's true. I just talked about it.
Yeah, I saw it.
I'm hoping it's true. Is everyone still awake? I can't see the whites of your eyes here, so I need to ask. So pressure sensors. So there's 2 ways we measure pressure on a vehicle. One is what's called gauge pressure. So if I go get a tire gauge, it's reading gauge pressure. Or if I go get a compression gauge or a vacuum gauge, it's going to read gauge pressure. So what gauge pressure means is that at atmosphere, or at whatever the atmosphere is where I'm at, my gauge is going to read 0. And my gauge only reads the difference between what atmosphere is and whatever I'm measuring. So it automatically compensates for whether I'm in Denver or whether I'm in Death Valley. Okay, so it's automatically compensating for that because it's always zero, and we're only measuring the difference between zero and whatever I'm trying to measure. The other way we have of measuring is using absolute pressure. So our MAP sensor stands for manifold absolute pressure, means it's measuring all the pressure. So typically we think of pressure being divided into either pressure or vacuum, vacuum being pressure less than atmospheric. For many pressure sensors on the vehicle, they read absolute pressure. So they don't distinguish between vacuum and pressure. All they're reading is pressure. So at sea level, our atmospheric pressure is 14.7 psi, means I have 14.7 pounds per square inch pushing down on me right now. So that is what I'm dealing with. If I go to Denver, which is higher, there will be less weight of air pushing down on me because there's less above me. I've climbed 5,000 feet. If I go to 10,000 feet, there'll be even less pressure on top of me. So the pressure sensor, we can do a couple different things with it. I can measure a differential in pressure. The MAP sensor measures an absolute pressure, but I can use a differential in pressure between 2 points in the system to detect flow or pressure change. But this 14.7, it's also 1 bar or 29.92 mercury. And that's at sea level. So you're going to hear me use that term 1 bar because a lot of European vehicles use bar. Bar is 1 barometric pressure or 14.7 psi. So it's fairly easy to convert. And 14.7 seems to be one of those magic numbers we come up with a few different times in automotive. Pressure sensors can monitor pressure differential between atmospheric and pressure within a component or system. And pressure sensors also monitor barometric pressure or altitude. So why do I care about the altitude? Well, because I need to put the correct amount of fuel into the engine. So as the pressure of air changes, so does the weight of air. Just like as the temperature of air changes, the weight changes. So we talked about temperature sensors. So now we're looking at pressure sensors. And why do I care about the weight of the air? How else am I going to figure out how much fuel to put in? Because I have to have the correct balance between air and fuel for the engine to run efficiently and cleanly. And so I know how much the fuel weighs. I know that at a certain pressure, if I inject fuel into an engine for a certain amount of time, I'm going to deliver a very specific weight of fuel. So we spend our time with our sensors on the engine trying to figure out and measure the weight of the air. So if I think I'm at 5,000 feet, but I'm here at sea level, I would be putting in what? I'd be running lean. I wouldn't be putting in enough fuel because the air here is denser at sea level than it is at 5,000 feet. So if my computer thought I was at 5,000 feet, but I'm driving down here at Pacific Beach, my car would not be running correctly. It would be running what we call too lean. It would not be getting enough fuel. And I could get check engine lights for that. I could also have some drivability problems or performance issues from that. On the other hand, I take off from here and I'm going to go skiing up in Big Bear for the day, which is, 8,000 feet. Well, once I get to about the 5,000 foot level, my car really starts losing a lot of power. I got black smoke coming out the tailpipe and it's running really, really bad because it's still putting out the fuel I needed at sea level. But now I'm at 5,000 or 6,000 feet. I'm running much too rich. So our car has to have the ability to compensate for that. In early days, we only compensated for altitude on startup. So it was not uncommon on 80s Fords, early fuel injected Fords, to be running out of power and barely moving By the time you got to, and GM had some similar issues, by the time you got about 6,000 feet above sea level. So you'd pull the car over, it's not running good, you'd shut it off, kind of stretch your legs, look underneath the hood, not that you knew what you were looking at, all this fuel injected stuff was all new. But then you get back in it, the car ran great, and you drove the rest of the way to go skiing, and like, gee, that was weird. Well, what happened is by turning the car off and restarting the car, it recalibrated for altitude. Today, vehicles are able to do that when we put our foot to the floor. So when we floor the vehicle, it recalibrates our altitude. So it also recalibrates on startup, but those are the two times it calibrates all altitude, which seems to have taken care of the other issue we had where it would, over fuel or under fuel. Because in Southern California, we can go from sea level to 9,000 feet on a single tank of gas. And the engineers in Detroit never thought about that because they really don't have mountains there and everything's really flat. So they didn't even think of the concept that we could change altitude so much in such a short period of time. So pressure sensors are 3-wire sensors. A 3-wire sensor has a reference voltage from the PCM, a ground, and a signal return or signal voltage wire. Doesn't that sound just like our TPS? A power, a ground, a signal return. So common pressure sensors used today are our manifold absolute pressure sensor, my fuel tank pressure sensor, because I need to check my fuel tank for leaks in case you left the gas cap off. Barometric pressure sensor, which may be built into my map sensor or may be separate. A delta pressure feedback sensor for the EGR. Ford used those for years. That measures 2 points in a system in order to check the flow of the EGR. But we also use delta pressure feedback systems and pressure sensors on diesels today to see is the diesel particulate filter plugging up? Is it time to do a regen? So there's a lot of stuff in diesel exhaust control and emission control where we use pressure sensors today. Fuel pressure sensors. So on modern vehicles that use direct injection, we're actually, and even some that don't, we're monitoring the pressure of the fuel in the fuel rail and actually using that pressure signal to control how hard we're working our fuel pump. So this is an example of some common sensors. I could get into AC. We have some AC pressure sensors that we use today. We have transmission pressure sensors we use today. I mean, I could make the list go on. I could put pages here. But I want to give you an idea. If we're measuring pressure, we're doing it the same way. So if I have a power steering pressure sensor with 3 wires, this is what we're going to do. If it's 2 wires, it's a switch. So if I look at my map sensor here, it's going to be connected to vacuum or connected to my intake manifold with a vacuum line, I should say, or maybe mounted directly on it. And it's going to have 3 wires, a power, a ground, and a signal return. And as the pressure changes on the diaphragm inside the pressure sensor, it changes the amount of voltage that we see on the signal return. So you can see it doesn't matter if I'm measuring fuel, if I'm measuring pressure, positive pressure, negative pressure, it doesn't matter, very small amounts of pressure. Then we're just into calibration because I'm going to move this diaphragm inside the sensor. And as the diaphragm moves, it changes the amount of voltage that comes out of the sensor on the signal return wire. So as we look here, here's the schematic. I have my VREF, and my VREF, it goes to EGR also, goes to TPS. From the PCM, remember I said we share those. So there is C is power in, ground is A on this one, so different pin configuration. So I should always drop 5 volts between A and C on this vehicle because I have 5 volts here, ground here. I only have a resistor in here. I should use all my voltage. B is my signal return. That is my digital multimeter that's just allowing me to get a signal back and measure what voltage do I get back. What's in based on that voltage, the computer interprets a pressure based on programming. Very, very similar to our TPS, isn't it? Matter of fact, I would argue that once we get out of the sensor and out of the computer, it is basically identical to a TPS. What do you guys think? Aren't both these circuits working the same way? Don't they both have power, ground, signal return? Don't they
I think
both
so.
all their
Yes.
voltage through the load?
Yes,
Yeah,
Yes.
true.
it's true. And this to me is fundamental, because this is not how the book really teaches it. You know, conventional is we go really deep in every one of these sensors and treat it like it's its own unique thing and completely different. And
They are
yeah,
three-wire
when
sensors.
what's that?
They are three-wire sensors.
Exactly. Power, ground, signal return. So I could test a map sensor same way I test a TPS sensor, right? Because I'm looking at power, ground, and is my signal return within the specifications for that vehicle,
Yes.
right? So I'm going to test it the same way. And that's why I didn't take the last hour to talk about how that diaphragm inside the sensor works and how it actually changes the electrical voltage and all that stuff, because I don't need to know that to fix it. Are you following the logic there? Need to know what it does, what it's measuring, what's it supposed to read, and verify it has all of its 5 volts. Now, Hall effect sensors are a little bit different. They're a 3-wire sensor. They are frequently used where accuracy and fast response are important. So this is a digital sensor that's going to produce a square wave. Gives a clear on-off signal. These are used places that, these could be places that rotate or places that move back and forth. So I could use this as a position sensor. No one does, because they're much more expensive than a potentiometer. So I don't necessarily use them as a position sensor for certain things, but this also gives me an advantage over a potentiometer for other positions. And we'll talk about that on the next slide. So it contains a powerful magnet. As the magnet passes over the dense portion of the trigger, the wheel, the 5 volts is pulled to ground, about 0.3 volts through a transistor in the sensor. When the magnet passes over a notch in the trigger, the 5 volts is restored. Hall effect sensors can be used for camera crank sensors, vehicle speed sensors, ABS sensors, brake position and clutch position sensors, power window sensors, sunroof sensors, just to name a few. So one of the advantages that the Hall has is that whether I'm moving really fast, like I need for a permanent magnet, or whether I'm moving really slow, it is still going to switch at the same point and with the same amplitude, whether I go by it really fast or really slow. So, and it puts out a square wave. So that's your, sawtooth pattern. Not sawtooth, I mean, it's just a regular square wave. And so as I push down, I can see it moved. I can see how fast it moved. I can see how far it moved. I can also see, like in the example of a clutch pedal, are you starting to let the clutch up? Are you letting it up slowly or quickly? So I can see this great amount of detail. Also, I can cut the notches at different sizes. So I can tell different things in the travel based on what I want to see. Am I getting close to the end? That kind of stuff. I can also count the total notches from one end to the other, so I know exactly where we are in the sequence. And so we use this technology in a lot of other industries for encoding, for encoders, setting location rings, things like that. So this is critical for start-stop technology, but it's also important for something like the brake pedal. Are you slowly applying the brakes, meaning you're gradually coming to the stop, or are you quickly applying the brakes, meaning we need to get into full panic mode here? So we're seeing where we used to just have a brake switch, the brake lights are on, brake lights are off. Some manufacturers are now investing money to put a Hall switch there where we can see exactly how fast it's moving, how far did you push it down, And also, if we have a car with start-stop technology, when the car's engine shuts off and we come to a light, when I'm letting off the brake, that's a clue that what? We need to start the car before you hit the gas. I need a Hall switch for that. Hall switches are all 3-wire switches. They're going to do power, ground, and a signal return. So the signal is going to look different than our previous two, which produce an analog signal. This produces a digital signal, but the rules still apply. I have power, ground, signal return. So Hall switches do a much better job of detecting movement at low speed compared to permanent magnet sensors. So permanent magnet sensors for wheel speed sensors don't really do under 3 miles an hour well, where Hall switches do. And that's one reason why we're seeing that movement to them. So here's an example here where I have a Hall switch for both my camshaft sensor and my crankshaft sensor. And let's take a look. I got reference low. Reference low is another name for ground. I have ignition feed. So we're feeding 12 volts into it. And then I have an output. So what do I got? I got power, ground, signal return. 3-wire sensor. My power is different. In this case, it's 12 volts instead of 5. And there's plenty of 5-volt Hall sensors out there also. But the principle is the same. Power, ground, signal return. So if I look at this, you can see I have 0 volts and 5 volts. And you can see I can have a pattern here depending on whether I'm measuring a camshaft, crankshaft, or whether I just spin around a distributor. So inside a distributor, I could have different size notches telling the computer which cylinder we're on. So now I don't need to spin around and guess or spin around to compare it to the crankshaft. I can know very quickly based on the size of the notch or the size of the hole exactly, was that number 6 that just went by or was that number 1? Because if I make them different sizes and tell the computer what the sizes mean, now I only need to turn the engine a little bit before I can start the engine. I don't need to wait for it to spin around twice. So if we can see each other and the blade's not in the way, I get 5 volts. When the blade comes through, it collapses the field, and I'm going to come down to basically 0 volts. High and low. So here's an example of an engine. And I have a crankshaft sensor on the bottom and a camshaft sensor up top. So my crankshaft sensor goes around twice. For every 1 time my camshaft sensor goes around. On this particular vehicle, they say that the camshaft is supposed to be the center of this. So I could take lines and draw a line from here to here and draw a line from here to here. And is it centered? Yeah, it's centered. So we're in time. If it wasn't centered, that would be a clue that I had a problem with my timing chain or some other component in the timing system, which would warrant further investigation and most likely disassembly. So here I'm using it where previously I showed you the permanent magnet sensor and a cam sensor. Here we're looking at 2 Hall switches where I have a crank sensor and a cam sensor. And you can see where lining this up gets very precise based on the manufacturer's specifications. So the manufacturer shows us how they're supposed to line up. And then we can go in and compare and see, is that correct? Much better than taking apart the engine. So here is a camshaft sensor. Ford calls this a synchronizer. So this used to be where the distributor was. They got rid of the distributor and put the cam sensor here. And if you notice, I got what? 1, 2, 3 wires. Power, ground, signal return. We know what power looks like. We know what ground looks like. And I just showed you what the signal looks like. It's a square wave. So really testing this is not much different than testing a TPS or testing a map sensor, is it? Power, ground, signal return. Do I have good power? Do I have good ground? Does my signal look like what it should? That's all I'm doing. If you notice, I didn't pull out an ohm meter here. I didn't start wires. Very basic. check for voltage across the sensor, check my signal coming out. Hall sensors generate what type of electrical signal?
A digital.
Yes, it does create a digital signal. Does it also create a square wave signal?
Yeah.
Yeah. So I'm thinking maybe number 4 here,
Oh, yes.
right? Because digital and square wave are two ways of saying the same thing, right? So, it'd be like, is there 12 here or a dozen here or 12 and a dozen? Yeah. So, and I put this question here not to confuse anyone, but I want to make sure it's clear in your head that these are the same. The other issue is different texts and different books will interchange these. And you're reading something and it's like it's totally different. And they're using the term square wave, and they always use square wave. Or there might be another book that just uses the term digital. They're talking about the same thing, but sometimes we get in the nomenclature. So if you don't know they're the same thing, it can get very confusing, or you think there's two different things out there going on. And that's why I reinforce this, because when I was learning this, there was some confusion, because I go to one class, they call it one thing. I go to another class, they call it another thing. And it took a while before I figured out they were talking about the same thing. And so that's why I wanted to combine this in and why I put these questions here. So here's a comparison. Here is my variable reluctance sensor or permanent magnet sensor. I get an AC waveform, and I'm going to have 2 wires going to it. It generates its own voltage and creates an analog signal. Here I have a Hall effect sensor with 3 wires, a power, a ground, and a signal return, and I'm going to get a digital signal out of it, or a square wave as we call it. Both are measuring a rotating component in this case. So these are the only 2 types of sensors we use to measure stuff that goes around. So if it's any kind of speed sensor, crank sensor, we're either using a variation of the Hall, which you see in the video I did. So they got a cute new name for it, but it's a modified Hall. I'm blanking on the name for a moment. I apologize. I think it's what is it? Anyhow. And then our permanent magnet. So all they're doing with the modified Hall is they basically have tied in the ground separately internally to get away with it. But they're, and a lot of times they're grounded through their mounting. But same technology. I'm either getting a square wave or a analog signal. If I see 3 wires, I know it's Hall. If it's 2 wires, it could be a modified Hall, or it could be variable resistance or variable reluctance, excuse me. The permanent magnet sensors tend to be bigger because they need that magnet and all those windings in there. So they tend to be a bigger sensor. Mass airflow sensor. Mass airflow sensor is the most common way we use to measure the air coming in the engine today. It's not the only way. So we can measure air coming in the engine 2 different ways. Either by weight, where we use the MAP sensor, or by volume, where we use a mass airflow sensor. The mass airflow sensor is the most common way we use it today. And it does have some of its own issues. So it is probably better at detecting issues, but it doesn't self-compensate quite the same way the MAP sensor does. So a lot of our lean mixture codes are on cars with mass airflow engines. So we get a lot of codes on these systems for fuel control. Most common type of mass airflow sensor used today is called a hot wire type. All hot wire type sensors use the same basic operating principle regardless of manufacturer. Mass airflow sensors use 3 wires. for their signal circuit, just like other 3-wire sensors we have looked at.
I'm liking this 3-wire thing. It's very helpful.
Yeah, thank you. So we may see some of these with up to 7 wires at the electrical connector, but there's still only 3 wires for the sensor. So what we do sometimes is I might have a 5-wire connector where I'm combining the air temperature sensor with the mass airflow sensor. I might make a 4-wire connector where I share the ground between the intake air temperature sensor and the throttle position sensor. So instead of running 2 wires, I'm combining it in the sensor, but I still have a 2-wire sensor and a 3-wire sensor. They're just sharing that sensor ground. There was some early stuff where they had 7 wires because they had the temp sensor, the throttle, the mass airflow sensor, and then 2 wires for a fuel switch. And it had to see a certain amount of volume or it wouldn't turn on the fuel pump. And that's on the old ones with a mechanical air door. So we do see some, but even though we may look at it, I want you to understand, if I see more than 3 wires, there's something going on more than just a mass airflow sensor. That's when it's time to get the book out. That's when it's time to start looking at the wiring schematic and see what that manufacturer did, because I only need 3 wires for the sensor. So if I got more wires than that, what else did they shove in this box that they're making it do? Did they put a temp sensor in there? Did they do something else weird? So that's, something to keep in mind, because I don't want you going on and going, I popped the hood of my car and it's got 5 wires. Okay, well, slow down a minute. If it's got 5 wires, that means there's more than a mass airflow there. What else is it doing? So they have a voltage reference, a ground, and a signal return. Gee, that sounds familiar. Although the mass airflow sensors work very different on the inside from the TPS and MAP, on the outside, electrically, they work the same. So many of the same electrical tests apply. Do I have power? Do I have ground? Do I have the correct pattern on my lab scope? Do I have the correct output, right? So do I have good power, VREF? Do I have good ground? And does my return, my signal return, look like what it should look like? And that's how we test these. And I don't care if I'm working on a Toyota or a Mercedes, I'm testing it the same way. So here's a picture of one on a BMW. There's a little mass airflow sensor. So here's where the air cleaner is. Here's the duct going to the throttle body, and here's our mass airflow sensor. The rubber is covering up the connector on it. So if I want to test a mass airflow sensor, I could use a voltmeter to check to see if I'm dropping 5 volts across it, or I could use a lab scope. But if I want to look at what the sensor is putting out, I want to use a lab scope. And what I'm going to do is I'm going to set a lab scope up on a 5-volt scale and 5 seconds of time. And with the engine running, I'm going to snap the throttle and let go very quickly. And when I do that, we get a sudden rush of air into the engine. And then air slows down for just a split second, because what happens is I just opened the throttle, I put all this air in the engine, but the engine hasn't sped up quite yet where it's ready for all that air. So there's a slight lag, which is what we see right here. And then as the engine itself speeds up, we're going to go over here and I need to get over 4 volts. And that's a good number, whether I'm working on a Toyota or a BMW or a Hyundai or a Ford. Okay, that is a good number. That's what it should do. Compare this with one I did that had a code. I'm doing the same test. So here I snap the throttle. It went up. We see it drop back down for the lag. Seemed a little more dramatic. And I only got to about 3 volts. What caused that to happen is the mass airflow sensor is dirty or it's out of calibration. Normally dirt is what causes a great deal of this. So a lot of times you can clean them and get them better. Sometimes it's in the circuitry on the board. If I have one that's set a code, I always replace the sensor and I always use a factory sensor. When I say factory sensor, that doesn't mean I'm necessarily buying it from Toyota. So for example, Toyota sensors are made by Nippon Denso. So if I can buy a Nippon-Denso sensor, that's the same sensor that it comes in the Toyota box, but it's coming in a Nippon-Denso box, and it's $100 cheaper, I'm buying the Nippon-Denso sensor. But it's the same sensor, so it's made by the same people that are making it for Toyota. Same with European vehicles. Like I'm going to buy a Bosch sensor for the vehicles that use a Bosch sensor from the factory, and save a little bit of money. Instead of getting that fancy Mercedes box, I'll get the yellow Bosch box for a couple $100 less. Same sensor. It's made by the same people. So I always want to go with whoever made it for the original equipment manufacturer. Now, as far as preventive maintenance goes, yeah, we clean mass airflow sensors all the time for preventive maintenance. And you want to use mass airflow sensor cleaner. That's what it's called. You don't want to use brake cleaner. You don't want to use carb cleaner. You don't want to use alcohol. You don't want to use anything else. You want to spend the $4 or whatever it is, $5, and get the can of mass airflow sensor cleaner. And although that sounds like a lot of money, most shops charge about a half-hour labor to do that. And they don't charge you for the chemical, which is nice, but a half-hour labor today is what, $60, $65? You know, $5 can seems like a good deal at that point. So a hot wire mass airflow sensor circuit works just like a TPS and map sensor from outside the sensor to the PCM. Is that true or false?
I'm still thinking.
You're still thinking. We shouldn't have to think too much. Would you just tell me? You said, hey, the 3-wire thing is helpful.
It's
Right?
true.
True.
It's true. Absolutely, it's true.
True.
And that's the point I'm trying to drive home. Once I know how a 3-wire sensor circuit works, and I know I have a power, a ground, and a signal return, I'm ready to start diagnosing any 3-wire sensor. Because I don't so much care about what's going on inside. I mean, that's good to know. So, example, on a Hall, if I don't have any signal on my signal return, is it a bad sensor, or did the wheel that's supposed to go around fall off and isn't there anymore, right? I mean, I can have weird things happen, but at least I know what my problem is in the sensor. It's not my wiring. It's not in my power supply. I know where the problem is. And that's where now it's time to take the old one out, do a visual inspection, do those kinds of things. Just like my map sensor. Say my map sensor isn't changing when I rev up the engine in like it should. And I've got good power and ground and my signal return isn't changing. That's a problem with the sensor. But guess what? If the vacuum line isn't hooked up to the sensor, it's not going to read correctly, right? So I still have to do my visual and make sure it's plugged, is connected properly, or whatever it's supposed to be sensing, it's still connected to. But this is real universal. It's just like my mass airflow sensor. I wouldn't want to replace the mass airflow sensor if the duct right after the mass airflow sensor has a big crack in it between the mass airflow sensor and the throttle body, because of course it's going to read wrong then, because there's a big hole where air is coming in that's not going through the mass airflow sensor. But this is really powerful because this allows you to really diagnose any 3-wire sensor, whether you're working on air conditioning, whether you're working on the engine, whether you're working on the suspension, you name it, because they basically work the same way. They have a power, a ground, a signal return. The question is, how much power are they supposed to have? And what kind of signal return does it get, right? Those are the things that we might need to look up or do a little research on. But you should understand how the circuit works at this point. And it's universal. I mean, that's kind of the secret sauce here, is that it's, I mean, I don't need to learn all these things in a vacuum. Even though we call them different things, even though they work differently internally and they're measuring different things electrically, once we get out of the sensor, between the sensor and the computer, they're the same. Power, ground, signal return, which means I can use that same diagnostic process on any of them. A mass airflow sensor can be tested with a lab scope, just like a TPS, true or false?
True.
True. I did just show you me doing that, didn't I?
Yes, you did.
Yeah, you're 100% right, Blake. Absolutely, that's true. You also see why I like lab scopes, because lab scopes paint a picture, right? And the pictures, like between the good and bad on both the TPS and the mass airflow, were what? Very visual, very obvious. We could see the difference between a good and a bad very quickly. So a 3-wire sensor circuit. I've got VREF, in this case 5 volts, ground. So here's my series circuit. Here is my signal return. It's going to send a varying signal out based on what the sensor is reading. And so I have test points at what? The computer, or test points at the sensor. Well, normally what's easier to get to? The sensor. So a lot of testing we're going to do at a sensor. There are some cars, there are some sensors. It's easier to get to the computer. But shouldn't I have the same thing here as I have here? Shouldn't this be electrically the same? Shouldn't here and here be electrically the same? Here and here electrically the same? So the reality is, once I know it's the same, it's supposed to be the same, whether it's at the sensor or whether it's at the computer, I'm going to test what? Where it's easiest. So I could spend an hour digging out a computer or 2 minutes getting to a throttle position sensor, which is a better test, the throttle position sensor. Also, what do you think they sell more of, throttle position sensors or computers? So you might as well. What's that?
Sensors.
Absolutely. So I might as well do my testing by the part that goes bad the most, right? I mean, what do you think they replace more of, mass airflow sensors or computers? Right? So I might as well do my testing where? At the mass airflow sensor.
Yes.
So I'm only going to test at the computer if I think I have a problem, like a high resistance on my VREF, high resistance on my ground, or a bad wire for my signal return. And if you think about it, I already showed you, if you have a scan tool hooked up, I've already probably got what? The voltage the computer thinks is there, so I can compare the voltage the computer sees to the voltage I see at the sensor. And doesn't that already do the voltage drop on this wire? Because if I have this the lab scope or meter here and I have the computer here, aren't we already comparing these 2 points without taking anything apart? And if I have 5 volts when I test between here and here, and I drop all my 5 volts across the load, I don't need to test this or this, because I already know they're good, because I'm dropping all my 5 volts across the only load in a series circuit. That means all the wiring has to be good. So the only wire at that point that's under question is this wire here. If I compare what the computer says to what my meter says right here, bingo, I just proved that whether that wire is good or not. So we can break it down pretty simply and test this stuff fairly easily most of the time. So if we compare these two, we talked about our 2-wire sensor. We're going to measure across the sensor, and we're going to see how that voltage changes based on temperature, based on switch position, based on, I could do it based on fluid level if I wanted, but no one's going to pour gas in a tank to measure. That's why we test the rest of the system on a gas gauge and not the level sensor. PCM signal input. Test point for ground, test point for signal return. Should always have 0 volts there. On my signal return, I'm going to be between 0.5 volt and 4.5 volts, depending on the resistance of that sensor. On my 3-wire sensor, I'm always going to have 0 volts here. I'm always going to have 5 volts here and here. And my signal return is going to vary between 0.5 volt and 4.5 volts. What we use for sensors is the 90-10 rule. We don't use the bottom 10% of the voltage range, and we don't use the upper 90% of the voltage range as a general rule. That's why you see that range in between 0.5 volt and 4.5 volts. An NTC type thermistor, the resistance goes up as the temperature increases. Is that true or false? An NTC thermistor is the resistance goes up as the temperature decreases. And I would ask you to think back to the lecture and what did I tell you the computer thought the temperature was if I disconnected the sensor?
Goes down. Temperature goes down. That's false.
That is false.
False. Yeah.
It is false because if I disconnect the sensor, which is an
Uh-huh.
open circuit, high resistance, the computer
Uh-huh.
thinks we're 40 degrees below zero,
Yes.
right? So I can't, the highest resistance I can get, I got a parka on. It's cold. That is how I always remembered this because I can never keep this straight in my head. So I just always went back to when I unplug the sensor, high resistance, I'm really, really cold. And then I can kind of think about that, and then I could work my way through the question. And like I said, that is how I remember it to this day. That's my cheat method because I can never remember this. I gotta always think, and end up thinking in the wrong direction, and I just gotta go stop. I unplug, it's 40 degrees below zero. Okay, that's high resistance. So if I'm not 40 degrees below zero, that means I have less resistance in the sensor. There you go. See, the problem is we think the temperature goes up being 200 degrees, 220 degrees, right? Well, if we're 40 below, 38 below is heating up, isn't it? Get to 10 below, it's time to take off my parka. Geez, getting hot. When testing an NTC type sensor, for proper voltage level of the signal, the positive lead of the DVOM or DMM should be placed on the signal wire and the negative lead should be placed on the sensor ground. Is that true or false?
Yeah, should be placed in the
Yeah.
signal. It's
True.
true.
Right? Because what am I measuring? I'm measuring my sensor wire, right? So I'm going to measure my sensor wire right here. So my positive lead has to go here. My negative lead has to what? Go to ground.
Mhm.
Absolutely correct. When testing a 3-wire sensor, there should be a reference voltage applied by the computer to the sensor. Is that true or false? It's true, isn't it?
True.
Yeah. So our VREF comes from the computer. On OBD2 vehicles, that's going to be 5 volts. The signal voltage of a 2-wire sensor is always measured on the wire between the internal resistance of the sensor and the PCM.
Signal voltage is to resistor. That's true.
That's true, right? Because that's the only place voltage is going to change is between our resistor and the PCM and our resistor and the sensor. And that's the wire we're measuring. When testing a 3-wire sensor, the technician should always read a minimum of 0.5 volts on the ground side of the sensor. Is that true or false?
That's true. False.
Okay. 3-wire sensor. What should
3-wire
always read on the
sensor.
ground side? 0 volts, right?
Good
Because what's my load? My sensor is my load. I have 5 volts going in, series circuit. My load has to use all my voltage. I better have 0 volts on the ground side. If I don't have 0 volts there, we have a problem.
Yeah, that's
Okay, and that does it for my sensor review. So let's look at some actuator circuits. So actuator circuits are things the computer uses to change an electrical thought into physical action. So normally done with electromagnetism, but we're talking about function and testing. And again, what I'm going to try to do, you see, we just went through all the sensors in the car, right? That wasn't so bad. You mean we ran a whole car with just those sensors? Well, yeah, because, and I didn't get the oxygen sensors, so that'll be a different discussion. But you think about it, I got thermistors, permanent magnet sensors, switches, That's it for our 2-wire. Then I got potentiometers, Hall effect, and then I got pressure sensors, which are MAP, my mass airflow sensors, which kind of a one-off, and my O2 sensor. And did I leave something out? Did I cover rheostat? Maybe rheostat. So we got what, 8, 9 different types of sensors in the whole car. Now we got 1,000 names for them. And if I drill down further, I look at 2-wire sensors, 3-wire sensors. 3-wire sensors, I can pretty much test them very similarly, if not exactly the same way. 2-wire sensors, I'm going to test very similarly. So I got 2 basic strategies I'm going to come in from testing, whether it's a 2-wire or 3-wire. So hopefully that drilled sensors down a little bit when we're looking at the whole car and you see all the different things. You know, we talk about ABS systems, we talk about lighting systems, we talk about all these really neat things, really high-tech stuff. We're going to be getting into engines, we're going to get into fuel systems and ignition systems. Keep in mind, we only have so many ways of doing something. And so it's just a matter of how did they repackage it today? So in our actuator circuits, most actuators are either solenoids, relays, or motors. All require 2-wire electrical connections, power and ground, right? If I want to work a load, I need 2 wires, power and ground. So an actuator circuit is going to be 2 wires. If there's more than 2 wires going to an actuator, we have another circuit. So there are some actuators, like a idle air control motor, that may have 4 wires going in it because there's actually 2 motors built inside there. Most rely on the principle of electromagnetism. By understanding how these work electrically, we can understand their operation and properly test them regardless of what name they're given. Light bulbs can also be an actuator because the computers turn on light bulbs on the dash, right? Our check engine light or our ABS light, airbag light. So really the big difference we have when it comes to actuators is how we control them. So we have a couple of different ways we can control them. So the circuit can look identical electrically, but can be controlled differently by the computer. So simple on and off signal. It's on, it's off. Pretty straightforward. Frequency. Remember, our frequency is a fixed amount of time it takes to repeat a pattern. So I can increase or decrease the frequency, which could change control. A duty cycle signal, which I'll go into, which is the amount of time a signal is turned on within a frequency cycle. And pulse width modulation, where we change both the timing of it and the amount of time we turn something on. So I'm going to go through these different types of controls because this is really what I need to know for testing. Because a load is a load is a load. Is it a motor? Is it a light bulb? Is it a relay? Is it a solenoid? If it's a load, it should do something when it gets power. So if I want to check if it's getting power, I need to understand the different ways we can apply power to it. And these are the different ways we use with a computer. So I could use a simple on-off circuit. So here I have an example of an EGR solenoid, a battery positive, a fuse, A, B, to pin 35 of the computer to a transistor inside the computer that'll supply ground. So when the computer grounds it, it turns on the EGR solenoid. If it turns it off, the EGR solenoid's off. So here, if I wanted to look for the signal, I would connect a meter or a scope here at B. Because with the switch open, I should have power here. And when the switch closes, I should have 0 volts or ground there. And I can see that happen with a scope. I can see it happen with the digital multimeter. I'm going to go from system voltage, 14 volts, whatever that is, to ground. And I'm going to see that on a meter because that's going to be on off. It's a slow signal. It's either on or it's off. So since it's a slow signal, I can see it with a scope or a meter. As we get into our faster signals, I have to use a scope to see it. So an actuator is either completely turned on or completely turned off. So you can see here I have my system voltage. The computer turns on the EGR solenoid. So I now have ground, which means it's on. When it turns it off, it'll pop back to voltage. Remember, computers are binary. They can only do ones and zeros. Everything is either on or off. I can't give you 6 volts. I can't give you 3 volts. Either I give you 14 volts or I give you no volts. That's our only options here. So frequency is another way we have of controlling things. And so a frequency is based on how many times a pattern repeats in 1 second. So here we're just measuring our pattern from the up to the up. And the number of times this repeats in a second is going to be my hertz. By increasing the frequency, increasing the number of times this happens, I can change the control of something. So here I can still measure this with a DMM or digital multimeter, DVOM, provided that my digital multimeter has the ability to measure hertz, which not all do. So I would need to be able to measure hertz in order to see this change. If not, I would need to use a lab scope. But you can do this with a digital multimeter, providing it can measure hertz. So that is hertz, and that is the definition of a cycle and of what hertz is, which is how many times we're repeating within 1 second. So frequency is defined by how many times a pattern repeats within what period of time?
Number 2.
Number 2, a second. So now let's look at duty cycle. Duty cycle is a measurement of time an actuator is turned on versus the amount of time it's turned off in percentage. So duty cycle is always going to be shown as a percentage. 100% means it's turned on all the time. 0% means it's not turned on at all. It should be this example on the next slide, and actually got a question after this, then we'll get to it. Normally, we're never going to 100%, and we're never going to 0%. It's normally somewhere in between because I still want that frequency. Duty cycle is a measurement in which of the following scales? How do we measure duty cycle?
Percentage.
Percentage. So as I look here, I have a cycle. In this case, my cycle is 80 milliseconds. From where I dropped here till I dropped here was 80 milliseconds. The amount of time it was turned on was 20 milliseconds. I'm using the cursors here to measure this. So 20 milliseconds. So 20 milliseconds is 1/4 of 80 milliseconds. So this it would be a 25% duty cycle. So my frequency is fixed. So my frequency is fixed at this 12.5 hertz that I measured when I measured the whole cycle. So this is happening 12.5 times a second. And as it's happening 12.5 times a second, this cycle, right now, 25% of that time, we're turning it on. So if I have something that I only want to turn on a little bit, I could use duty cycle. So where you might normally say, you know what, 12 volts is too much. Why don't we try giving it 3 volts? Well, if I'm at a 25% duty cycle here, that's exactly what I'm doing is I'm giving it 3 volts. Because keep in mind, we're turning this on and off very quickly. So kind of reminds me of, you know, we're getting it to stay airborne by keep touching it, right? We're keeping pushing. It's never getting back to the ground. So this is how duty cycle works. So we duty cycle a lot of things on the car. We use this for fuel pump control. So I can change how fast the fuel pump goes. I can use it for a purge solenoid. I use it for EGR on electronic EGRs. I use it for all kinds of stuff. We duty cycle. We use it for variable cam timing, a lot of different things. Duty cycle control is less expensive than the next type of control we're going to talk about, which is pulse width modulation. So, and for most things, it is perfectly adequate. So if I only want to say, I want to slow down my fuel pump, it's going too fast at 12 volts. So let's give it 6 volts because I don't need all the fuel that's making it 12 volts. Why wear out my fuel pump? Let me just give it 6 volts by using a 50% duty cycle. Oh, I need more fuel. Let me increase the duty cycle to 60%. Now we have more fuel. Or 70%. Now we have more fuel. And I still have that capacity for when you put your foot on the floor, I can go up and I can get more fuel. And those systems, they're never going to go to 90 or 95%. Most of those systems that use duty cycle to control the fuel pump know that we should never be going over 70% or 80%, whatever magic number the engineers pick. So if it does go over that in order to maintain fuel pressure, guess what? We're going to get a code. We're going to get a code that says, hey, there's something wrong with your fuel delivery system. Your fuel pump's working too hard. Is that a bad pump? Is that a leaking injector? Is that a fuel leak somewhere else? I don't know. Bad pressure sensor. I mean, it could be a lot of things. The point is we're going to get a code and the check engine light's going to come on telling me to take it in the shop before I'm walking with a broken down car. So we have ranges that we use for these duty cycles. And when the duty cycle gets out of that accepted range that the engineers put in when they built the car, we start getting codes for things. So that's really kind of takes the place of a sensor almost at that point, because now we're getting that, we're able to look at that command signal and say, I'm working too hard to do what I'm supposed to do. There's something wrong. Bing, the check engine light comes on, time to go into a shop. And that happens before the system completely fails. And so that's another reason why manufacturers use duty cycles, because they're able to use that command as the ability to set codes based on how that system performance is normally supposed to be. So the last one I want to show you is pulse width modulation. So pulse refers to turning an actuator on and off, and width refers to the amount of time the injector's on or the device is on. Modulation refers to the fact that the actuator is being controlled or modulated over a period of time at different frequencies. Pulse width modulation is different from duty cycle in that both frequency and on time varies. With duty cycle control, the signal frequency never changes. And this is an important point because many manufacturers will call duty cycle control pulse width modulation, and it's not. And you don't know that till you hook a lab scope up and go, wait a minute, this is duty cycle. So manufacturers will flat out put the wrong stuff in their manuals and in their training because they use words inappropriately to what they actually are. So why do I care about that? Because I need to know how to test it. I also need to know that if I'm looking to test it one way based on what the manufacturer tells me and I hook my scope up and it looks completely different, I need to understand what my scope is telling me and that the scope's not lying to me, the manufacturer did. And now I can go about diagnosing the system. So many circuits don't need to ever change the frequency, right? We just control our on time, vary the voltage to it. However, other things on the vehicle do need to change their frequency, meaning how often I do them. Probably the best and simplest example is the fuel injector. So if my car is idling at 400 RPM, 400 revolutions per minute, I am going to fire the injector 400 times in that minute. So we could calculate that out to 60 seconds and then calculate out what the frequency is, which I'm not going to do. Now I've raised my engine speed up. And my engine is now doing 3,000 RPM going down the road. So now I have to fire that same injector at 1,500 times a minute. And I can take that back down through the 60 seconds and so on and come up with a frequency. And what we'd find is that frequency is a higher frequency than the one we started with. I'm firing that injector more often, more times a second, higher frequency. So I've changed my frequency. I've changed literally when I'm firing the injector. I'm no longer just how much of the time do I fire it, but I'm doing it the same amount every time. I'm now responding to the engine speed, and therefore I have to change the frequency of when I fire the injector. So that's why I use the injector as an example of that. It's because that we use pulse width modulation to fire injectors today, but also you can really kind of illustrates the point about how that time has to change. I'm doing it more often because my engine's going faster.
Mr. Brian.
Yeah.
So that's pretty much, it applies also to, let's say, spark plug coils.
Mm-hmm.
So it's the same thing.
Absolutely. I'm going to change the frequency on the spark plug coils. I may even change the amount or duration that I saturate the coils to get a different amount of spark. So absolutely, I'm going to pulse width modulate my coils. So absolutely, we do that. So in this example, so this is a fuel injector is turned on once per engine cycle. However, the engine's RPM increase, so does the frequency of turning the injector on and off. The following illustration, the injector is turned on for 6.85 milliseconds. So here's my pulse width. We're controlling the ground side of the load. So I have system voltage. When the computer connects the ground, it goes to 0. When the computer disconnects the ground, the voltage goes back up. So this is the amount of time that we turn the injector on for, that we flowed current through the windings right here. And when we brought the cursors over, that's how we got the time in milliseconds. Now, here is our system voltage, 14 volts, whatever. If you notice, my voltage went up really, really high here. That is because we flowed current through a coil. When we collapse or stop current flow through that coil, it creates what we call an inductive kick. And that's that high voltage that we see here. So this is 0 volts here. So this is 14. So it's 5 volts per scale. So 5, 10, 15, 20, 25, 30, 35, 40. So we jumped up to 40 volts for a split second when we collapse the current flow through that field. So we'll get into more of that when we get into ignition, because we actually use that inductive kick in order to make spark on the ignition system. But when I flow current through a coil like that, and then I collapse the circuit, I'm going to get an inductive kick. And those inductive kicks can get over 200 volts. So they can get pretty high. So you got to make sure you have equipment that can handle that. Pulse width modulation is measured in which of the following?
Second.
Not seconds.
Oh.
Well, yeah, I guess you're technically correct. I mean, I did measure it in milliseconds, so we can do that.
That's why I
So,
said
so that's so you are correct. It's not the answer I was looking for. What I was looking for was on time. So that's the phrase we use, is on time. But you're right, that on time is seconds. So you're right. You're 100% right. We are measuring it in time. It's just not what I was looking for, and that's not your fault. It's my fault for writing a bad question. In duty cycle, the frequency never changes, but in pulse width modulation, it does. Is that true or false? In duty cycle, the frequency never changes, but in pulse width modulation, it does.
But in pulse.
It is true.
True.
Remember, the difference between duty cycle and pulse width modulation is in duty cycle, the frequency never changes. But in pulse width modulation, both the amount of time we're turning it on and the frequency change. So this is true. So as I look here, actuator power supply normally comes from 12 volts.
Okay, within hot.
So we're not supplying 5 volts to these. These are normally connected to battery power. The computer normally controls the ground. Now, there are some manufacturers, Honda and Chrysler, that'll supply ground to the actuator, and the computer controls the power. And we call that high side control. And my scope pattern would look exactly the opposite, because we would have no voltage. And then when we turn it on, we'd get voltage. So here I'm measuring 12 volts at the power supply side of my actuator. I should always have system voltage there. And if I go to the other side, we're going to see what? Either duty cycle control or pulse width. We're going to see something happen. And if we're pulsing it with the engine running, then I should see something between 0 volts and my system voltage, depending on what my duty cycle is. So if I'm on duty cycle control at 50%, I'd see half battery voltage. If it's pulse width modulation, because we're turning on for such a short period of time, I may only see a volt. I may only see very, very little. So it's not an accurate way of measuring performance. But what it will do is it will tell me if it turned it on, because otherwise I would see 12 volts all the time. Now, a word of caution here. My voltmeter only updates every 200 milliseconds. We only turn an injector on for 6 milliseconds. So it's completely conceivable that your meter may not even notice it, may not even see it happen. You can try using min max on the meter to make it a little more sensitive and maybe catch something. But it is possible you could hook a meter up, the car is running, and yet you see no change because it's happening too fast for the meter to detect. That's why we use scopes. So here, this example, I got that 5.5 volts, just kind of demonstrating somewhere between 0 and battery voltage, we are going to see a varied voltage. Doesn't really give me a lot of information. It may not give me any, depending on what's going on. Compared to a scope, now I can see exactly I had power. We turned it on for this long. I got the inductive kick. And now we're back down to battery power. And you can see the inductive kick here. What, about 60 volts, a little over 60 volts on the inductive kick. So a lot more. So if I'm using min max, I'd get, if it picked it up, I'd get close to 0 volts and I'd get 60 volts. Tell me what? Yes, it did fire, and yes, I got something, but boy, this is not on for very long. I mean, I'm on a 20 millisecond scale. So this whole screen is only 20 milliseconds. And so as we're looking down through here, this is 4 milliseconds to here, 8 milliseconds to here. So what are we talking about here? We're talking a millisecond that's high, 2 milliseconds that high, when my meter only updates every 200 milliseconds. Good chance I might not catch a lot of this that's happening.
Can it be augmented?
What do you mean augmented?
Like zooming on the screen for when you're taking the reading, and we're only doing 20 milliseconds. Can it be stretched to have more detail?
Oh, could I zoom in more on this?
Yes.
Oh yeah, absolutely.
That way we get more detail.
Right. So I could change this to 10 milliseconds, 5 milliseconds, whatever amount of detail I want to see.
But what I said makes sense, right? With zooming or the opposite, we will get more detail.
Right. So I can zoom in, look at a shorter amount of time will give me more detail. If I look at a longer amount of time, I'll see more of the picture. So the question is, am I looking for a missing fence board? I might want to stand away from the fence, right? On the other hand, if I'm looking, does the fence need to be painted? Now I want to get really close to it to see if it needs to be painted, right? So
Yes,
I'm
yes.
looking at the same fence, but it's what information am I trying to get? And so my goal is to be getting to play with some of these scopes when we're on campus in September. So I've already got some lab exercises and some simulator boards to get you guys kind of used to doing some of these tests and used to doing some of these tools. So it looks like at this point, we will be on campus on Mondays, is what it looks like. So I had some people last week ask about scheduling. It looks like every class is going to get 1 day on campus, and it looks like our day is going to be Monday.
Starting when again?
Starting in September. It starts the week of the 7th, so we would be the 13th would be our first day.
Okay, September 13th.
So not as much as I'd like, but I'm thankful for what we're getting. And I've got a lot of hands-on trainers and hands-on stuff, and I have enough of them that we should be able to certainly be working no more than 2 people to a group. Depending on how many people we have, it may be 1 person to a group. So that's gonna give you guys a real chance to get some hands-on stuff. The exercises I'm looking at, we're going to be dealing with electrical and sensors and things like that. So I have different simulators, including a engine vehicle simulator that we can do all the testing with, that we'll do some lab scope with. So we'll get to do some meter and some lab scope use. It'll really
Do you
get.
think it would be possible for students that took previous classes? Like for me, I finished Mr. Jackson, so I never got to use the alignment machine, the balancer machine, all the machines from suspension and alignment.
Right. Yeah, and the discussion is, do I think it's going to be possible? Yes. Do I know exactly when it's going to be possible? No.
Yeah.
I think we're going to have a better idea as we move through September, because classes cycle again on October 11th, I think. And so there may be some ability at that point to have previous students sign up for just the lab portion. So I'm not sure what that's going to look like, because we're getting well above my pay grade. But that discussion has been had. Everyone's in agreement that we need to make some accommodations for that. I don't know of the logistics on it yet. One thing that was brought up, well, hey, we could do it in the afternoons and a separate thing. Well, then it comes down to, how do you get people paid? There's just a whole lot of, how do you get staffing support? How do you do all those things?
Yeah,
So that's what we're trying to balance out and get that figured out. But I did want to give you guys a head up, because I'm doing the schedule in for approval. And on the initial schedule I was asked to do, we have Mondays. So that is, that's what it's looking like. And I told you guys I'd get to you guys as soon as I know something. It's not 100% confirmed yet, but I have a feeling that that's what it's going to be, since I've already talked to my boss and my boss's boss, and they were both good with it. So I still got to wait for the formality of it. But it looks like that's what's going to be happening.
Well, we're moving slowly but surely. That's a good thing.
That's a good thing. I can't wait. So tomorrow we're going to finish up on actuators, and then we'll probably start getting into engines. So the rest of actuators goes fairly quick. I do have those labs in Canvas where I did the sensor testing. I did 2 of them, one on the simulator and one on the vehicle. Highly recommend that you guys take a moment and look at those today and do those assignments today. That way, while we're in this module, if you guys have some questions based on the videos, tomorrow will be a great time to talk about them.